So we're going to take the integral from pi over 6 to pi over 3 of sine of x to the cosine of x to the sine of x minus cosine of x to the sine of x to the cosine of x. And right away what we notice about this integral is we are not going to take the antiderivative of sine of x to the cosine of x to the sine of x, right? That's just ridiculous. There's no way that we have an elementary antiderivative of this kind of function. So what we're going to have to do is use the fact that this is a definite integral to our advantage to try and turn this into something that's easier to deal with. And to start out, I don't really want to consider both of these terms at the same time. So what we're going to do is use the fact that we can split up the integral into two parts to make this two separate integrals just like this. So we have the integral of sine of x to the cosine of x to the sine of x, and then minus the integral of cosine of x to the sine of x to the cosine of x. So let's consider just this part of our integral right now. The integral from pi over 6 to pi over 3 of sine of x to the cosine of x to the sine of x. Now, what you'll notice is this part of the integral is very, very similar to this part of the integral. They have the same form. The only difference is that we switch the sine and cosine. In this one we have sine of x on the bottom and then cosine of x, and then here is cosine of x and sine of x, and here it's sine of x and cosine of x. So we've taken the sine and cosine and switched them around. So what that suggests is the way that we're going to deal with this integral is to transform this into something that's more similar to this one. And in order to do that, we notice that we have sine of x and cosine of x, which are two very closely related functions. So let's see if we can look at what the fundamental relationships between sine of x and cosine of x are, and see if those help us in evaluating this integral. So a couple of the fundamental relationships. One is that the sine squared of x plus the cosine squared of x equals 1. Is this going to help us at all? Well, in order to use this identity, we would have to write the sine of x as the square root of 1 minus cosine squared of x and do the same thing for cosine of x. And that's just going to make our integral really ugly. So we don't really want to do that because that's going to make it really hard to actually evaluate what we're looking at. So let's see what the other fundamental relationships are. Another one, what is the definition of cosine of x? Well, one definition is that it's the sine of pi over 2 minus x, right? That's why it's called a cosine. It's the complementary sign. So it's the sine of the complementary angle. Now this is something that we can use a lot easier because we see without doing any fancy algebra on this, we can immediately plug this identity into our cosine of x right here and change it into a sine, which is what we want in our resulting integral. And we also know that we can flip these two functions around. We know that sine of x is also the cosine of pi over 2 minus x. So these two, again, we can immediately plug them in. So let's see what happens. We get the integral from pi over 6 to pi over 3. Sine of x is the cosine of pi over 2 minus x. And then cosine of x is the sine of pi over 2 minus x. And then we do the same thing for the last one up here, and then dx. And now we see that this integral is basically in the form of what we want, our second part. All we need to do now is change this pi over 2 minus x into just an x, which means we're going to do a substitution. Let's let u be equal to pi over 2 minus x. And that will give us that du is negative dx. So if we plug this information into our integral, pi over 2 minus pi over 6 is going to give us pi over 3. And pi over 2 minus pi over 3 is going to give us pi over 6. And then we have cosine of u to the sine of u to the cosine of u. And then dx is going to become negative du. Now we notice that what happened when we did our substitution is that the bounds switched. We had pi over 6 to pi over 3 before, now we have pi over 3 to pi over 6. But because we have a negative du, what we can actually do is multiply this entire integrand by negative 1 and flip the bounds. So we can change this so that it's from pi over 6 to pi over 3, and then we just take away this negative sign, and this will be the same integral. And now we have exactly what we wanted before. We have cosine of x to the sine of x to the cosine of x, and we even have the same bounds. And remember that because we're doing a definite integral, it doesn't matter what variable we plug in here. It could be u, it could be v, it could be a, but it could also be x. So this is actually equal to the integral of cosine of x to the sine of x to the cosine of x dx. That'll give us the same answer. So what we see is that our integral from sine of x to cosine of x to the sine of x is actually equal to the integral of cosine of x to the sine of x to the cosine of x. So we have something minus the same thing because these two are equal. So if we take something minus itself, the only possible answer that we get is 0. So when you see an integral like this that has some crazy stuff that you know you're not going to be able to evaluate normally, you want to start looking at, especially if you have two closely related functions, what are the relationships between those two functions that you can utilize in order to transform this integral into something that's easier to deal with. So that is our answer.